Now we're going to do the same thing, the same pattern, but look at what happens when you want to graph cosecant, secant, and cotangent. Okay? Because cosecant is just 1 over sine. And so now that we've learned the steps of how to graph 1 over anything, we can graph cosecant. So now we're back to our trig unit. You have to remember what your sine graph looks like. And I have it, draw the graph of the bottom first, so that's sine. So here is our sine graph. And the first thing you would look at is, do you have any x-intercepts? You have a lot of x-intercepts. And everywhere you have an x-intercept, you're going to have a vertical asymptote. I have one there. I have one here. Oh, we have lots of them. So wherever there is going to be an x-intercept, you're going to have a vertical asymptote. We can label these a little bit. Maybe I won't label them all, but this one's at x equals 0. This is x equals pi, x equals 2 pi, x equals negative pi, and so on. We could label them all if we wanted to. Next, in reciprocal graphs, we ask, does our graph go up forever or down forever? Because then we would have an asymptote at 0. But this one doesn't, right? It doesn't go up forever. In fact, the biggest it ever gets is 1. It doesn't go down forever. The smallest it ever gets is negative 1. So we don't have to draw an asymptote at y equals 0. The next thing we look at is nice points. So on this original one, can you see that here you would have pi over 2 comma 1? And, for example, you know your unit circle, you would have pi over 6 comma half. What's going to happen on the reciprocal graph? Because sine of pi over 6 is a half, right? Oh yes, you do need to know your unit circle for the exam. They'll give you a little one at the beginning that you can fill in. So since I know that sine of pi over 6 is a half, what's the reciprocal going to be? 2 over 1, or 1 over 1 half, which just becomes 2. Does it make sense that this one is going to stay the same? You're going to have pi over 2 comma 1 again, because you do 1 over 1. And if your graph has to go towards asymptotes, does that make sense in that section? And once you've done one section, you'd be like, oh, well, wherever it's 1, it's going to stay the same. And wherever it's negative 1, it's going to stay the same. It has to go up towards the asymptotes because reciprocal graphs never have x-intercepts. And this is the graph of cosecant. It's the same rules that we did earlier, right? Where you have x-intercepts, you have vertical asymptotes. This is the first one where we haven't had a horizontal asymptote, though, because our graph doesn't go up forever, doesn't go down forever. But the same idea with nice points. You find a point, all you do is change the y value to 1 over the y value. So I'm going to get you to do the secant graph right over top of the cos graph.
Hello.
Hello.
Hi, is Brayden in class?
No, he is not.
Okay, thank you.
Oh, my mic was on mute. So the first first part of this video will be very quiet. How did you do? The secant graph looks very similar to the cosecant graph because the cos graph and the sine graph look so much the same. When graphing it, really the only nice points you do have to label are where it's 1 and -1. I mean, you could have said, right? Oh, let's do this one here. With cos, you know that cos of pi over 3 is 1/2. So you would have pi over 3 comma 1 over 1/2, which is the reciprocal is 2 over 1. You would have that point as well. And then finally we get to the cotangent graph, which has a couple of its own special rules. So this is the most complicated one coming up. The cotangent graph. So cotangent is 1 over tangent. Cotangent is also, if you remember, cos theta over sine theta. And this is important because it adds a slight change to this graph. So we're going to start by doing things the same as if we did all of our steps. Do we have x-intercepts? Yes. If we have x-intercepts, you can't divide by 0. Those will be non-permissible values. So wherever we have x-intercepts, we're going to draw asymptotes. And there's going to be quite a few on here. I probably didn't need to graph it to 4 pi. But there we go. Lots of asymptotes. This is going to be the busiest looking graph. Because already it's looking busy with all the asymptotes on it. Okay? Now, here is exceptional rule number 1 for cotangent. Next, you would normally draw a horizontal asymptote. And you would draw a horizontal asymptote if your graph goes up forever or down forever. And tangent goes up forever. And it also goes down forever. So according to the rules, we should have a horizontal asymptote on this one. But cotangent doesn't. And the reason cotangent doesn't is because when they decided how they were going to graph cotangent, they had to decide, are we going to graph 1 over tangent, or are we going to graph cos over sine? And they're very similar, but slightly different. And one of the places where they're slightly different is if you graph cos over sine, there is no horizontal asymptote. So for cotangent, there's going to be no horizontal asymptote. We are going to do nice points. Like, for example, on tangent, you know that when you have tan of pi over 4, you get 1.
So for 1 over 10, would there be holes on top?
If they said graph 1 over 10, then yes, you would draw an asymptote.
There's always going to be holes in there?
And actually, it's not even an asymptote, they're going to be holes.
Okay.
It's a little complicated. Okay? Cotangent and 1 over 10 are a little complicated. Okay? So for cotangent, of course, for tangent, you have pi over 4 comma 1. Does that make sense? That point would stay the same. In fact, wherever tangent is 1, cotangent is 1. So we're going to go across and label nice points at all the y values that are 1. And the same thing when the y values are negative 1. 1 over negative 1 isn't going to change either. Okay? Here's the other difference between cotangent being thought of as cos theta over sine theta and cotangent being thought of 1 over tan theta. When you have 1 over tan theta, there would be no x-intercepts. When you have cos theta over sine theta, you could have the top equal to 0, right? Think of your cos graph. Is your cos graph ever equal to 0? Yes. Where is it equal to 0? It's equal to 0 at pi over 2, at 3 pi over 2. In fact, wherever the tan graph had asymptotes, your cotangent graph has an x-intercept. So that's a special rule for the cotangent graph. Because you have to think of it as cos over sine, and technically it's not 1 over 10. Okay? Now, if you graph, once we've got those x-intercepts and we have the other points, can you see that if you graph towards your asymptotes, that your cotangent graph is like a tangent graph just twisted the other way, with asymptotes. Yeah. The dotted lines in the middle that were printed, that are labeled underneath, those are your asymptotes for tan. But if you think about, does it make sense? Remember that tan is sine of theta over cos of theta? So your non-permissible values for tangent are where the bottom is equal to 0, where cos is equal to 0. So your non-permissible values for tangent become the zeros of cotangent. And this is the final graph. Technically, the graph of 1 over tangent, instead of having x-intercepts, would have holes. So if you wanted to graph, the graph of cotangent doesn't have holes, but if this question said, and they'll never do this on the exam, but if they ever said graph y equals 1 over tangent, it would be exactly the same, but each of these would have to be holes because they're non-permissible values still as well. But that's getting extra complicated. Okay? The cotangent graph is very, very rare. In my 20-some years of teaching, 2 exams per year, it has happened on the exam once. Does that mean that they're itching to do it again? I don't know. Is it due? I don't know. But it has happened once in the last 40 exams.